So my talk is about the energy ahead of us and how integrated solutions, and specifically, working, having the electric grid, integrated with the gas grid in very complementary ways may be our most resilient and feasible and affordable way to get to net zero here in the Maritimes. This conference is about the strategic transition to electrification, which is really the means to achieve emissions reduction, which is the goal. And so in talking about the gas grid and integrated solutions, I'm not trying to be provocative. I'm being very supportive of the strategic transition to electrification. But I also want to be pragmatic in that Nova Scotia's goal is to reduce emissions by 53% by 2030 and to get to net zero by 2050. And like running a marathon, getting to the halfway mark takes about 20% of the effort. And getting from the halfway mark to the finish line takes about 80% of the effort. And I think in trying to get to net zero, that's going to be similar as well, that if we really are serious about pushing beyond our 2030 targets and getting to net zero by 2050, it's going to take a real kind of all hands on deck approach, because we use a lot of energy in the Maritimes, and only about 20% of that energy today is clean. And to get to net zero, almost all of that energy is going to need to be clean within 25 years, which makes this a really pivotal time for us in the energy industry here in the Maritimes. So to get to net zero by 2050, we're going to have to transform this whole energy system that we have today. And we're going to have to do that while we also continue to meet growing energy demand. Our population is growing, our economy is going to continue to grow, and even with energy efficiency, we're likely to still need more energy. So we're going to need to use every tool that we have available to us. So we're going to need a lot more energy efficiency. We are going to need electric vehicles, both battery electric and fuel cell electric. We're going to need heat pumps, electric heat pumps, maybe gas heat pumps, perhaps hybrid heating systems as well. And we're going to need a lot more low carbon energy. But getting to net zero, especially here in the Maritimes, is still going to be a massive challenge, because we use a lot of energy, about 288 petajoules today. That's about 80,000 gigawatt hours of energy, and 80% of it is fossil fuels. And we use this energy for many different purposes. About 40% of our energy is used for transportation, about 24% for light transportation, but 16% is heavy transportation. We use about 20% of our energy in the residential sector, another 20% in the industrial sector, and then 16% for commercial and institutional buildings. And like I said, by 2050, this is almost all going to have to be clean, which is a long way to go, because today, while we use lots of different types of energy to meet our demand, like I said, most of it is fossil fuels. So we use electricity to meet 30% of our energy needs. About 2/3 of that is renewable, but the other, or is clean. The other third is not. And over 50% of our energy use or energy demand today is met by refined petroleum products, either gasoline, diesel, or heating oil, and then about 14% comes from natural gas and propane. And like I said, almost all of this by 2050 is going to have to be clean. And we think, and we hear a lot about the way we're going to get to net zero is we're going to clean the electric grid and we're going to electrify everything. And I think that's partly true. But because when you look at many of our energy uses, they can be electrified relatively easily. So sectors like light transportation, heating, many residential and institutional and commercial buildings, and even some of our industrial processes can be fairly easily electrified. But not all. There are many other energy uses that are going to be very difficult to electrify, or at least very difficult to electrify with batteries alone. So these sectors like heavy transportation and high temperature in industrial processes where you need combustion, like to make a brick or to make steel. And some commercial and institutional buildings, especially really big and really old ones, might be really difficult to heat only with an electric heat pump. And the reality is that these much more difficult to electrify sectors currently represent about 1/3 of our total energy use. But we're going to have to figure out how to decarbonize them too. So regardless of sort of what the path to net zero is going to be, we are going to need clean electric grids, and we're going to need a lot more clean electricity. The Canadian Energy Regulator has forecast that here in the Maritimes, electricity demand is going to grow about 60% between now and 2050. And so just to put that in context, to keep pace with growing electric demand, we need to build another hydroelectric facility the size of Muskrat Falls every 5 years until 2050. That's how much more electricity we're going to need. And even if we do that, it still won't likely be enough. And part of the reason for that is that a lot of the increase we're projecting for electricity is going to be renewable, and those renewable sources like wind or solar are intermittent. And when we add a significant amount of intermittent renewables, it creates challenges trying to balance supply with demand. So if you have too much supply, you either have to store some of that supply or curtail. And if you look here, this is the wind farm near Amherst. And I don't know if you noticed, but I drive to New Brunswick a lot, and sometimes you'll drive by on a beautiful summer day, and the wind is blowing, and these aren't turning. And you think, why aren't they? Because we don't need that power. We have already as much supply as we need to meet the demand on those days. But to get to net zero, we shouldn't be doing that. We shouldn't be curtailing power unless we absolutely need to. In Nova Scotia's Clean Power Plan that was just released a month or so ago, they're calling for the addition of about 1,600 megawatts of additional wind onto an electric grid that has current capacity of about 2,800 megawatts. So like more than 50% more capacity coming from wind. And so then you think, okay, so what do you do? How do you balance supply with demand? Battery storage will help, especially to meet kind of short-term imbalances between supply and demand. The upgraded intertie with the New Brunswick power grid, that will help. But it's still not going to be enough. And as a result of that, from Nova Scotia Power's latest integrated resource plan, they're forecasting that 30 to 40% of the potential generation from wind and solar will be curtailed through a combination of wind integration constraints, transmission limitations, or just balancing supply and demand. So times when supply exceeds demands, especially in the fall and in the spring. But we can do stuff with that power. So what's the solution? I'll say, first of all, there's no one solution. I think that we know that. But one of them will be that in addition to having a lot more clean electricity, we're also going to need other types of clean energy. Types like green hydrogen that can be produced at large scale and then stored and transported and used in many of the ways that we use fossil fuels today. One of the reasons why fossil fuels have been the backbone of our energy system for over 100 years now is because you can store that energy for a long period of time. And especially in a northern climate, we're always going to have that need. We're always going to need more energy in the winter than we do in the summer. So we think that building a much more integrated energy system with an electric grid and gas grid working together in complementary ways is going to be a better way to get to net zero than trying to do it all with only electricity. And we see the more integrated energy system with linked electric and gas grids working together will also build a more flexible and a more resilient energy system. And I'll talk about that a bit in a minute. But fundamentally, we kind of have to start with two foundational principles. We've heard a lot about this today. Energy efficiency and conservation has to be job one. We need to do all we can to use less energy, conserve what we have, make our buildings better insulated, put in heat pumps when we can, convert from internal combustion vehicles that are about 20% efficient to electric vehicles that are a lot more. So that should be job one. But then we're also going to need cleaner electric grids and a cleaner gas grid. And we see the gas grid kind of playing three very complementary roles to the electric grid in this kind of more integrated low-carbon energy system. The first way that the gas grids can support the electric grid is through peak demand mitigation. Because as we electrify more end uses like heating buildings, transportation, industrial processes, peak electric demand is going to grow. Even through energy efficiency and all that stuff, that's going to help kind of have it grow not as much, but it's still going to grow significantly. And it's going to be a bigger problem in the Maritimes, even than other parts of Canada. So in Ontario, for example, their electric grid peaks in the summer. Ours peaks in the winter. And it probably, at least unless climate change gets to the point where winters here aren't cold, our electric grid is still going to peak in the winter. And this is one of the areas where the gas grid, especially the lower carbon gas grid, can play an important role. And let me try to illustrate this. This chart shows total natural gas demand in HRM for a full year back in 2021. We have about 50 megawatts of base load demand. So that's demand that's for domestic hot water, industries that are basically running 7 days a week, 52 weeks of the year. In the winter, average demand for gas is about 250 megawatts, so about 5 times higher. Not surprising. On cold winter days, it goes about 350 megawatts, so about 7 times higher. And we actually, you'll notice here, on the peakiest day, it was actually about 8 times higher. But the reality is, unless we want to be cold on that peakiest day, we need energy for that day too. The good news is that the gas storage and transmission and distribution system has really kind of been built to address peak demand. We can store enough gas, whether it's fossil natural gas, renewable natural gas, or other low carbon gases. You can store it in massive quantities. And unlike a battery that can store energy for a few hours or a day or two, you can store that gas for an indefinite period of time. Frankly, you can do that with oil and gasoline as well. That's why we have these massive tanks. We don't like them, but the reality is they can store energy for a long, long period of time. So that becomes important. And then you think, okay, so how does the ability of the gas system to do this complement electrification? Here's one example. So in a hybrid heating scenario, for example, electric heat pumps are an excellent and very efficient way to heat most buildings on most days. But on the coldest winter days, when the coefficient of performance of the heat pump drops significantly, just as demand for electricity begins to skyrocket, that causes a huge spike in electric demand. And in Nova Scotia Power's integrated resource plan, they obviously look at many, many different scenarios. And one of the scenarios they looked at was hybrid peak mitigation. See, how much of that electric peak do they think that they could mitigate with a hybrid heating solution? And what they determined is that there may be significant cost savings to heat many, if not most, buildings with a hybrid system rather than 100% electric. And the way that this would work is, so you have an electric heat pump, and probably 80% of the or more of the heating demand for that building is met with the electric heat pump. But on the coldest days, when peak electric demand goes up and the efficiency of the heat pump drops, at some point the smart control takes over, shuts the electric heat pump off, and turns a backup boiler or furnace on. And that, frankly, could be run by any kind of fuel. Typically, it would be gas of some kind, whether that's natural gas, renewable natural gas, green hydrogen potentially, or even propane. And that backup system would heat the building on those peak days so that the electric utility doesn't have to have this kind of standby capacity available that's only needed on those really cold days. Another potential solution in certain kinds of buildings are gas heat pumps. And gas heat pumps work essentially in a very similar way to an electric heat pump. They transfer heat from the air inside the building and can do that without putting much strain on the electric grid. At Eastwood Energy, we're currently involved in 3 different projects to test different types of gas heat pumps in different kinds of buildings. We have one for large multi-unit residential buildings, one for smaller MERBs, like in the kind of 4 to 12 unit range, and we're also starting a project testing a gas heat pump in single-family homes. This is a 140-watt gas absorption heat pump that we've installed in a 65-unit apartment building in Halifax. And I'll say at the outset, I'm not saying that a gas heat pump is better or worse than an electric heat pump. It really depends on what the application is. So electric heat pumps generally have a higher coefficient of performance, and where they can do the job, they're probably the best solution. But in many existing buildings, especially older buildings that have a hydronic system and aren't very energy efficient, a gas heat pump might actually be the better option. A gas heat pump, it does operate similar to an electric heat pump, but it only uses about as much electricity as a hairdryer. So that means that, while lots of buildings will have electric heat pumps, and on cold days, electric peak will go up because of those, a building that has a gas heat pump is not going to experience that peak. One of the other benefits of a gas heat pump, again, in the right kind of building, is it can essentially be a drop-in replacement for an oil or a natural gas boiler. So there's minimal additional capital. So often if you're retrofitting a building, especially an older building, to put in an electric heat pump, the cost of the electric heat pump is only a small portion of the cost. Often you're having to convert a hydronic system to a different kind of system, or doing a significant energy retrofit of the building envelope to ensure that it can operate effectively within an electric heat pump. Conversely, a gas heat pump like this one can just be dropped in, connects directly to the hydronic system in the building, and can provide both space heat and, in some applications, domestic hot water as well. The second area where we feel the gas system can complement the electric system is in the area of resiliency. Almost all the natural gas infrastructure here is underground, so it's not vulnerable to severe wind events, which we experienced a lot of, and unfortunately with climate change, we're experiencing them even more frequently. So as a result, a typical Eastwood Energy customer would experience a 1-hour service interruption every 70 years. So again, if you think about an electric grid that is increasingly vulnerable, think about how can that gas system kind of support the electric grid. And then the third area where we feel the gas grid can play an important role is to help decarbonize sectors that are going to be hard to abate. And so low carbon gases like green hydrogen and renewable natural gas can help decarbonize these sectors, like heavy transportation, especially long-haul heavy transportation, high-temperature industrial processes, and maybe some buildings as well. So we're doing a lot of work now on green hydrogen to try to determine its best applications here. And we really believe that green hydrogen is going to have to play a role if we're serious about getting all the way to net zero by 2050. And we think that because you can produce green hydrogen at large scale. You can store it for long periods of time. You can move it around, especially within relatively small areas, like within HRM. And kind of the way to think about green hydrogen is much like electricity. So electricity is not energy, right? Electricity is an energy carrier. And so when you use electricity, it doesn't emit any GHGs. The emissions associated with electricity come from the way you produced it. So if you produce electricity with coal or oil, obviously the emissions associated with using those electrons are going to be high. And if you produce that electricity with renewable energy, the emissions are going to be extremely low. And hydrogen works much the same way. So hydrogen is also an energy carrier. It's carrying energy in a molecule rather than an electron. If you produce the green hydrogen with non-renewable energy, while there aren't any emissions from the combustion of that hydrogen, there are emissions associated with its production. But if you produce the hydrogen through electrolysis with renewable electricity, then like with green electricity, the emissions associated with its use are extremely low, if not zero. And that's where most of the focus here is in green hydrogen, partly because we have a great wind resource here, both onshore and offshore. Green hydrogen can also play an important energy storage role. So again, think back to those wind farms that are being curtailed in the spring and the fall. If we weren't curtailing that energy, but letting them run full speed, we could use that surplus renewable electricity to produce green hydrogen and then store it for times when we're going to need it, especially in the winter. And so the way that this works is, you use typically a renewable energy source here. Like I said, it's probably going to be wind. You use that renewable electricity in an electrolyzer that splits water molecules into hydrogen and oxygen. You can then store the hydrogen in tanks or underground. And you can also blend it with natural gas in the natural gas system and distribute it that way. And then you can use that hydrogen essentially in all the ways that you could use natural gas today. And this is sort of what a facility might look like. This would be about a 5 megawatt electrolyzer facility. It would produce about 100,000 gigajoules a year of green hydrogen. And the sectors where we think it's going to play the most important role, especially in the short term, is in the heavy transportation sector. And we use 1.3 billion liters of diesel in the Maritimes every year. And most of that is for heavy trucking, transit buses, and marine applications. And while some of these transportation applications can be electrified with batteries alone, hydrogen fuel cells are likely to be a more practical zero emissions alternative, especially for long haul trucking, trains, long transit routes that are kind of beyond the range of a typical battery electric bus, and with some marine vessels as well. And this is not to say that batteries or fuel cells, that one is better than the other. They both have unique advantages and disadvantages. And that really determines the best application. So for passenger and light-duty vehicles, for example, that sit idle for 90 to 95% of the time, they generally drive short distances. I know we get really concerned about range anxiety, but if you really think how many times a year is that a real concern, you can usually count them on one hand or even one finger. And also for applications that don't carry a lot of load, batteries are likely to be, well, already are, the most practical option. But in the heavy transportation sector, both batteries and fuel cells are likely going to have a role to play. The fuel cells have the advantage of a lot more range, like typically, similar range as you would get with a diesel vehicle currently. You can refuel a fuel cell vehicle in about 10 or 15 minutes. And they don't lose as much range when it gets cold. So you think in the trucking sector, for example, if you have a drayage truck, today it's going from the port of Halifax over to Burnside and then back, and it's just doing that route back and forth. Battery electric is probably going to be fine. It's as long as you can kind of take it out of service for 8 to 10 hours to recharge it at night, it's going to work fine. But you take that same truck and say now it's going from the port of Halifax to Ontario, and it has a range, if it's battery electric, of 200 or 250 Ks. It's going to get from here to, say, Moncton, and then it has to stop and has to recharge, not for 10 or 15 minutes, but for like 8 or 10 hours. So like day one is to Moncton, day two to Edmundston, day three it goes a little bit further. That just does not work in that kind of application. Conversely, a fuel cell electric truck will have a range of probably 400 to 500 Ks. And when it gets to when it's depleted, the hydrogen that it stores on board, it will refuel in 15 minutes and then keep going. So those are just kind of some of the ways you need to think about, when would you use one versus the other. It's also important to understand that a fuel cell vehicle is an electric vehicle. The only difference is that in a battery electric vehicle, you're storing electricity in the battery and using that stored electricity to run the electric motor. Whereas in a fuel cell electric vehicle, you're storing hydrogen on board and running the hydrogen through a fuel cell to produce electricity. And then it still runs that same electric motor. So if you look at a bus, for example, a battery electric bus and a fuel cell electric bus look almost the same. They have about 90% of the same parts. They have the same drivetrain. Really, the only significant difference is that on fuel cell bus, you've got these tanks on top that are storing high hydrogen, and with a battery electric bus, you also have batteries. That's the fundamental difference. So then you think, well, why would a bus be battery electric versus fuel cell electric? Again, it depends on the same kinds of considerations. If a Halifax Transit bus is operating on a fairly dense urban route, like on the peninsula of Halifax, a battery electric bus is going to be fine. It makes lots of stops. It doesn't go that far. But if you put a battery electric bus on a route like the one that goes out around the Sambro Loop or out to the airport and back, one run is 100 Ks or more. And so that battery electric bus might only be able to run that route once or twice before you have to take out of service now for 8 or more hours to recharge it. Conversely, a fuel cell electric bus on those types of routes can basically be a one-for-one replacement with a diesel bus. So that's why transit agencies like Halifax are looking at, they're committed to transitioning to a zero-emission bus fleet, and that fleet is likely to be some combination of battery electric and fuel cell electric buses. So while hydrogen is obviously in its infancy, and we've heard a lot about hydrogen in the last couple of years, and I'm optimistic that within the next 2 or 3 years, there will start to be green hydrogen available here. We can also produce other types of low carbon gas, like renewable natural gas, which is made from organic waste. So think of green bin waste, landfill waste, wastewater. And these projects as well can essentially, kind of the way that I think about this is, if you buy, say, green choice electricity, the electrons are exactly the same, but you're ensuring that the electrons that you get came from a renewable source. Renewable natural gas is much the same. You can't distinguish a molecule of renewable natural gas versus fossil natural gas, but the way it's produced is much different. So in applications where you've determined that it'll be very difficult to electrify, especially a natural gas process, you could purchase renewable natural gas, just like you purchase green choice electricity, and not have to do anything else. It's basically a drop-in replacement. So there are facilities in Canada that are doing this now. This is the Surrey Biofuels facility out near Vancouver. It takes green bin waste, runs it through an anaerobic digester that produces biogas, and then that biogas is upgraded by removing nitrogen and other impurities, and that renewable natural gas then can just be blended into the natural gas system, and molecularly it's exactly the same as fossil natural gas, but every gigajoule of renewable natural gas you produce displaces a gigajoule of fossil gas. So to bring this all home, this is sort of how this more integrated energy system could look here. So if you look on the left-hand side, you see different ways we can produce energy through wind or solar. The blue lines on this chart represent the electric grid, and the yellow line represents the gas grid. So when you have wind and solar available, you can obviously use that renewable electricity to go directly into the electric grid. And that's probably what you would do for light transportation, to heat many buildings, and if you had a little bit of surplus, you could store it in a battery for a short period of time. Conversely, you could use that same renewable electricity in an electrolyzer to produce hydrogen, and then use that for heavy transportation, high temperature industrial processes, and if you needed to store it, you could store some of that for long durations of time. So that's the way we see it working. So you see, we're not trying to say one type of energy is better than the other. I think to get to net zero, we're going to need it all. We're probably going to need it all and then some. The challenge is figuring out what's the best type of energy to use for the right application at the right time. But I just want to conclude with a quick story about sort of what the future might look like here. But this, in the northern part of Great Britain, they are starting an ambitious project called H21. And H21 is a project to convert the gas networks in the northern part of the UK from natural gas to hydrogen starting in 2028. And there are a lot of parallels between what they're doing and what we could do here. The city of Leeds, which you can see here, has been proposed to be the first entire city in the UK that will convert its natural gas system over to a hydrogen system. And it's a really interesting case study for us because Leeds is a northern city. It's about twice the size of Halifax. It has a winter peaking energy grid like we do. And the natural gas grids in Leeds and here in HRM and in New Brunswick as well for that matter are also similar in one really critical way. And that way is pipes, and specifically plastic pipes. Though hydrogen is best transported and distributed in plastic pipes because it tends to leak through, especially older steel and iron pipes. And the reality is that most gas distribution systems in North America and Europe, have been built 75 years ago or more. There's some parts that are really new, but some parts are really old. And the older parts tended to be built with steel and or iron pipes that are not really compatible with the distribution of hydrogen. So what Leeds is doing is they're in the process now of converting all of their old steel and iron pipes over to plastic pipes. But conversely, the gas distribution system in the Maritimes has all been built within the last 25 years. And almost all of it has been built with yellow plastic pipes. So this means that we probably have the most hydrogen compatible distribution system anywhere in North America, right here. And so there are things that we could do with hydrogen, even in the short term, that most other gas utilities in North America or Europe can't do, or at least can't do without this kind of a replacement. I'm going to end there, and I'm happy to take any questions.
So when do you expect to get the results back from these kind of pilot case where they're tested? I assume it's 100% hydrogen through those pipes, or is it like a blend, or?
They will start with a blend. So there are, you can blend up to about 20% hydrogen with natural gas without it affecting the safety or performance of the equipment that uses natural gas today. Once you get beyond 20 or 25%, at some point you actually have to either replace the burner tip of the boiler and a building, or eventually completely convert that equipment. So one of the things they're talking about doing in Europe is, they're already developing natural gas equipment that is hydrogen compatible, and at some point, probably within the next 10 years, they will mandate that all new natural gas appliances have to be hydrogen compatible. But Leeds, their goal is to completely switch out the system. That's their goal. I'll say, it obviously comes with other challenges, because if you're going to be distributing 100% hydrogen, then all of the equipment that uses that needs to be hydrogen compatible. Ted?
Yeah, just to build on that, where are we with equipment in North America to get beyond the 20%? Are there, in terms of regulations?
Well, two questions. So where are we from a regulatory standpoint? So I'd say where we are from a regulatory standpoint is that most provinces have approved blending up to about 5% currently. Dalhousie University is actually just starting a really interesting project to test higher and higher blends. So we've been working with them, and their project will test blends of hydrogen and natural gas up to 25 or 30%. And what they're trying to see is at what point you start to run into safety or performance issues with a whole variety of natural gas equipment, furnaces, boilers, ranges, generators, those types of things. So that's kind of more on the regulatory side. On the equipment side, the reality is today, you can't buy a hydrogen-compatible boiler or generator here today. Europe will likely lead the charge. There are places in the world now that are already distributing relatively high blends. In Hawaii, for example, they've been distributing about a 15% blend for 50 years. And it all runs through the same equipment. You go to Home Depot, buy the same equipment, operates that way. Singapore as well has a gas distribution system with a fairly large or high blend of hydrogen. Yeah?
Anyway, just to add to the conversation, what you said about using hydrogen when and where is properly used,
Right.
when it's really needed. For example, a couple of weeks ago we were in Orlando on the AEECE World Conference, and we had the opportunity to chat with Balearia, which is a big shipping company with large ships for shipping, right? Across the Atlantic and in the Spanish Peninsula. And Naturgy, which in fact is a company like this, Plus for Energy, and they sell hydrogen, they sell natural. They in fact determined, just made the conclusion that hydrogen is not something that the ships will be using. Like that, said because for long trips. Why? For short trips, okay, maybe. But for long trips, it doesn't make any sense. Right? Why? Because you will store. You will need too much capacity of your ship just to store the
Right.
hydrogen.
Yeah, so
or you make money shipping stuff, so it's where the money will go. So they started to change that concept and said, well, you know what, let's try to use hydrogen in the operations of the shipyards, right? But not necessarily on the ships. It's giving them very good results, right?
Right.
So,
yeah. I mean, it's interesting in the shipping sector. You know, that's another sector that, you know, today runs on bunker sea oil for the most part. And it's going to have to be decarbonized. I think the shipping industry's concluded what you're saying. It's not going to be hydrogen in a gaseous form and probably not even a liquid form. It's probably going to be ammonia or green methanol, which is a derivative of that. Partly because just to get the sheer amount of energy onto that ship, that's what you're going to need. And if you look at the projects that Everwind and Bearhead are developing here in the province for export, they're also not planning to export gaseous or liquid hydrogen. They're planning to export ammonia.
and in fact they say, for example, for shipping ammonia, that it makes sense that the ship runs with ammonia because you are using the facility itself, which is a ship, which is almost a small city,
Right.
just to run, and definitely that helps with the emissions. So, but it's like you said, use the hydrogen where really makes sense, right?
Right.